Okay, then let's start. I think it's time. So, just to introduce myself, hello everyone. I'm Sushila. I am a PhD student associated with the Systems and Control Group at IIT Bombay, and I'm also the TA for the course EE90. So, let's start with the third week tutorial session. So, I hope you can see the screen. Okay, so let's just start with recalling the concepts that were discussed in the third week. So, one of them was modeling of DC servo motors, in which we did one of them was constant free current modeling. So let me just do IF equals constant, and the other one was the armature current being held constant. Then we saw how to convert a state space model to a transfer function, and there were basically two approaches to it. One was just the direct application of the formula. So J is equals C times SA minus B inverse B plus D, and the other one was just write this down because the Lagrange algorithm. And the third part, this was not done in the third week lecture, but there's a question about it in the assignment. This is the state transition matrix. So just to give you a hint, this is used for finding the solution of x dot equals ax plus b. Alright, so let's start with the second part of the third week. So let's begin. The first one is the conversion of state space model to transfer function. Alright, so let's look at the first question. So derive transfer function. I'm just going to write derive GS for the following state space model. So let's begin with the first one. So it's a second order system, 0, 1, minus 2, minus 3, plus 1, 0, u, and the output equation is 1, 0, x. So there is one thing that you can observe, that this seems like the CCF form, the state space model. So let's just see what the transfer function is going to be. So G of S, which is I of S over U of S, is going to be C times Si minus A inverse B plus A. So this is already 0. So for a 2 by 2 system, calculation of this inverse is pretty simple. So let's write this down. Let's write what is Si minus A. So this is going to be 0, 1, minus 2, minus 3. So this becomes S minus 1, S plus 2, and S plus 3. Alright, so for the inverse of a 2 by 2 matrix, what you can do is interchange these two entries. Sorry? Uh, yes. Okay. Okay. So interchange these two, and for this, what you can do is interchange the sign. So let me just write this down. So Si minus A inverse is 1 upon determinant of A, and the adjoint of A, which I'll just explain it to you, would be S plus 3 S. So let me just do this really. Um, so this ends here. This is actually adjoint of Si minus A. Right. So this becomes 1, and this becomes minus 2. So we have S times S plus 3, and then we have plus 2, again the same matrix. So we get S square plus 3S plus 2 times this. And now we already have C and B, so let's just substitute them in GS. So 1, 0, or I can just take this factor in common. So 1, 0, S plus 3, 1, minus 2, and S, and B is 0, 1. Oh, sorry, it's 1, 0. Okay, so let's just remove this. That this is not the CCF one. This is going to be actually 1, 0. So let's just compute this. S plus 3 and 1. So this is simply S plus 3 over S square plus 3S plus 2. Okay, so just as a check that if it's a second order system, just check that the degree of the denominator is also 2. So you can at least be sure that you get the same order system. Now let's move on to the next part. It's also a second order system. So let's see, x dot equals minus 3, 1, minus 2, 0, and this is x plus b times u, and the output equation is still the same. So we have the A matrix. Let's just determine what is going to be Si minus A inverse. So 3 1 minus 2 0. Get s plus 3 minus 1 2 1 just s. So si minus a inverse become s times s plus 3 plus 2. So the denominator is still the same as in part A. So we have s plus 3 and just 1 and minus 2. Alright, so the transfer function becomes 1 upon s square plus 3s plus 2 1 0 and then 0 1. So this becomes s and 1. Let me just check again. Alright, so this is just 1 over s square plus 3s plus 2. Alright, so again second order system. Now let's look at another question. So we have some second order state space modules. So let me just write it down. The first one, so I'm just going to write the matrices directly. A is minus 2, 1, 1 and minus 2. B is 1, 1. C is 0. Okay, so let's see what the transfer function is. So D is 0. Then we have s plus 2 and minus 1, and s plus 2. Alright, so we have s plus 2 squared minus 1, s plus 2, these are still the same, and then we just do sign inversions of the off diagonal elements. So this is s squared plus 2s plus 1, s plus 2 1, 1 and s plus 2. Now let's see. S squared plus 2s plus 1 and 0 1. Then we have S matrix times B. Sorry. Oh, so just 3, right? No, 4 minus 1, 3. So this is just the second row. 1 s plus 2. This is just 1 plus So let's see if we can simplify this further. So what I'm going to do is use this here. So it's a square minus b square. So we just expand this. So we have s plus 3, s plus 1. This is simply 1 over s plus 1. So you can see that even though this was a second order system, the transfer function that we got after pole-zero cancellation was of order 1. Alright. So let's just see another example. So again we have the ABCD matrices. A is minus 1, 0, 0, minus 3. B is 1, 1. C is 1, 0. So now let's quickly compute. Let's see. X plus 1, 0, 0, 1, x plus 3. So this is a very simple case. There are no off-diagonal elements. So Si minus A inverse is simply s plus 1, s plus 3, and then interchanging the main diagonal elements. Okay, so then g of s is, so let's not expand the denominator just now. So it is 1, 0, and then 1, 1. This is going to be just the first row. This is 1 over s plus 1. So again, this is a second order system, but the transfer function is of first order. And observe that this is the same transfer function that we got in the first part. So this is a, just note that the transfer function of a module is unique. However, as we just saw that there are at least two state space representations of the same transfer function. So the state space model is known. So again, as a check, you can see that there is also a third part to this question. So I'll leave it up to you. There are again the three the state space matrices: minus 2, 0, 0, minus 1. Then B is now 0, 1, and C is 0, 1. So check that the transfer function say GS equals 1 over S plus 1. So from these questions you can note that there are three state space representation for the same transfer function. Alright. So if this observation is clear, let's move on to a third order system. Let's see, this is question 3. following states is null. So I'm just going to write down the matrices. X dot is 2 minus 1 0 1 1 2 minus 1 0 1 x plus, so minus 1 0 1 0 0 2. Then we have y equals 1 1 0 1 0 1 and 6. So you can already see that this is a difficult system to solve, not in just terms of the order, it's a three third order system, but also it's multi input and multi output. So there are two inputs and two outputs. I'm just going to write multiple outputs. Okay, so instead of uh, calculating the transfer function using this equation, let's just use the algorithm. So let's first see the steps. Alright, so sorry about that. We're still going to use this, but using the Levy algorithm, we're going to compute Si minus A. Okay, so let's just start. Step 1, we have given as 3 by 3 identity matrix, and alpha 1 is going to be trace of A. So let's compute this. 2 plus 1 plus 1. Okay, so now let's move on to step 2. So P2 is going to be P1 times A plus P1 times I. Sorry, so this is A1 times I. This becomes A plus A1 times I. We have 2 minus 1 0 1 1 2 minus 1 0 1 4. Alright, so let's compute P2. So it is 6 minus 1 0. So there are no changes in the diagonal elements, and 0. Okay, so this is going to be 5 and 5. So we have P2, then A2 becomes, so we have trace of P2 times A. So with a negative sign, so there's another error, this is going to be minus. So let's just compute this again. We'll have minus 2, minus 3 and minus 3. Alright, so let's compute what P2 times A is. So I'll just do this here instead. Minus 2 so it's minus 2 minus 1 0, 1 minus 3 2, minus 1 0 minus 3 times a. So this is already here. 2 minus 1 0, 1 1 2, minus 1 0 1. Alright, so let's compute minus 4 and minus 1. Okay, so we have minus 5. Now we have the second entry, it is 2 minus 1. So let's write this in directly. And the last one is just minus 2. Then we have 2 times minus 3 times minus 2. So we have minus 3. Then we have minus 1 minus 3. Then we have minus 6 plus 2. Then for the last row, it is minus 2 plus 3. Then we have just 1. Then it is minus 3. So you can recheck these calculations again. Then trace of P2 times A is minus 4 minus 5 minus 4 and minus 3. Alright, this becomes minus 12. So A2 is minus half minus 12. So this is 6. Okay, so this we have the last step. This is just a third order system. So we have P3 equals P2 times A. We have already calculated this plus A2 times I. So let's write this down. We have minus 5, 1, minus 2, minus 3, minus 4, minus 4, 1, minus 3. So 6 on the diagonals. So P3 becomes 1 minus 2 minus 3 minus 4. Okay, so since there will be changes only on the main diagonal element, so let's compute those. We will have plus 1, 2 and 3. This is P3, and for A3 we need minus half, again trace of P3 times A. So let's compute. Begins. Trace is trace is minus 12, so A2 is plus 6. It's minus half trace of P2 times A. Yeah. Okay, so let's compute A3. So for that we need P3 times A. Okay, so let's compute this. 1, 1, minus 2. And A is already here, so 2 minus 1 0, 1 1 2. Okay, so let's compute now. Okay, so the first element is 2 plus 1 plus 2. Alright, then the next one is minus 1, this is just 0. We have 0 and 2 and minus 2. Alright, so this is the first row. Then we have minus 6, plus 2 and plus 4, so 0. And then we have 3 plus 2, sorry. And then the last entry is going to be uh, so it's still 0. Alright, now let's compute the last row. We have 2 plus 1 minus 3 is still 0. Then we would have minus 1 plus 1, and we have as the last element. Okay, so it's a diagonal matrix. Okay, so A3 is just minus half trace of P3 times A. This is going to be, sorry, 15, right? Okay, sorry. So we have all the elements now. Okay, so now let's write down the transformation. Sorry, the xi minus a inverse. Okay. This is going to be p1s square plus p2s plus p3 upon, this is going to be s cube plus p1s square plus a2s plus a3. Okay, so let me just see what the denominator is going to look like. S cube plus, so a1 is minus 4, minus 4s square, this was plus 6, and minus 1. Now let's just compute the numerator. So s square times p1. Alright, so this is just so plus s times p2. So let's just quickly scroll up. Okay, this is minus 2 minus 1 0, and then we have p3. So, okay, so let's quickly compute this. This is going to be s square minus 2s plus 1. Just 1 second. Okay, then 0 and minus s plus 1, and it is a minus 2. Okay, then 0, sn minus 3, we have s square minus 3s plus 2, then 2s minus 1. Okay, so then we have minus s plus 1, then just 1, square minus 3s plus 3. Okay, so let's see what the matrix C was. We have 1, 1, 0, 1, 0, 1. Before that, let me just write down the denominator. So 1 over s cubed minus 4s squared plus 6s minus 5. Okay, now let's write down C. And then we have this matrix. And then finally we have B. So it's minus 1, 0, 0, 0. So let's just check if this is dimensionally correct. Alright. So this is s cubed minus 4s squared plus 6s minus 5. Okay. So the first one is s squared minus 2s plus s. And then we have minus 2. So then we just add these. It is s squared minus 4s plus 3. And then 2s minus 6. Then we add the first and the last element of each column. So we have s squared minus 3s plus 2. Then we have 2 minus s squared minus 3s plus 1. Okay, so let's just write this down. This is going to be 3 by 2. Let's see. Okay, so this is going to be negative, and so let's just write this down. Minus s squared plus s plus 2. So this cancels out. We have minus 3s plus 5. And then this is just 4s minus 12. Just 1 second. I think there's a problem in the dimensions. Sorry about this. Okay, so this is the last entry is just 2s squared minus 6s plus 2, and the first one is minus s squared plus 3s minus 2. So we have minus s squared. Okay. So you can see that GS is just not numerator divided by denominator. We have two inputs and two outputs. So you can see this as y1s over u1s. Then we would have the output y1s due to the second input. And we would have y2s over u1s and y2s over u2s. So you would have 4 entries corresponding to this 2 by 2 matrix. Alright. So if this is clear, now let's move on to the next question. This is question 4. So again we have a third order system. So let's see. So I'm just going to write down the matrices directly. This is 0, 1, 0 and 0, 0, 1, minus 6, minus 11, minus 6. Okay, so you can compute Si minus A inverse in by any of the methods that you wish to. So just 1 second, let's see. So let's compute Si minus A inverse manually without using the above algorithm. So we have Si minus A. Let's write this down. So this is just okay. So minus 1, 0, 0 minus 1, plus 6 and plus 7. So S and S plus 6. Alright. So let's see what is the determinant. It's going to be S times S square plus 6S plus 11. And then we'll have plus 6. Let's see, S cube plus 6S square plus 11S plus 6. Alright, now let's quickly get the adjoint of the matrix. So before adjoint we need the cofactor matrix. So you can denote this by this. Let's see. So the first one is going to be plus times just this one. So S square plus 6S plus 11S. And then we will have minus 6 just seconds. This is 1 1 1 2 1 1 3. Alright, so the last one is going to be just minus 6. So you can compute this alongside me if you want to recheck these calculations. Then we would have alright, so negative of minus S minus 6. Yeah, that is it. Then this would be s times s plus 6. This would be negative of 11s plus 6. Now we are at the last row, so it would be 3 1. This is just 1. Then negative of okay, minus of s, and then the last entry will be just s square. So let me just rewrite this again. S square plus 6s plus 11s minus x minus 6s. Okay, so now you have the adjoint. This is just the transpose of it. So this is going to be s square plus 6s plus 11s minus s minus 6s. Second row and okay, so let's see. Um, okay, for this, right? So let me just okay. So this is just 11s plus 6 and the negative of it. This is fine, right? And this is going to be 2. No, you have this and this removed. So this, yeah, okay. This is right. Yes, okay. And the last column would be 1s and square. Alright. So we have Si minus A inverse. Let me just write the GS directly. So C for this is 451. Sorry, let me just write down the denominator. S cube plus 6s square plus 11s plus 6. Then we have 451. Right, then this big matrix. S square plus 6s and then B is sum to 0 0 1. So I'm going to write this part first. It seems easier. So 451, and then we just have 1 SMX4. Alright, so this becomes just I'm going to write this down here. So it's s square plus 5s plus 2. Okay, so you can recheck again if the calculations are incorrect at some point. Okay, so now you have seen two ways to calculate Si minus A inverse. For a second order systems, it's pretty simple. You don't have to come to these two methods. There is just let me just scroll back up. Yeah, there's just this method to compute the adjoint. So for third order and higher order systems, so you may need to resort to the algorithm, or you can just compute SI minus A first. Alright, so if this is fine, let's move on to the next question. Just a second. Okay, so this is question 5. Okay, so first of all, this is a second order systems, and I want you to try this out. So this is A minus 2, 1, 1 minus 2. B is 1, 0. And C is 1 minus 1. Okay, so just tell me first what is SI minus A inverse for this, if you can compute this now. Okay, so is this what you've got? Okay, and I think there is one other student, you can check too. Let me just see what the name is. Yeah, it's I think Rajiv. Yeah, did you get this one too? Okay, this is fine. Then let's just compute this DS. Or maybe let's see this if there are any 4-0 cancellations. So then we have C 1 minus 1 is plus 2 is plus 2 now, and then 1 0. Alright, so this is just S plus 2 and 1. This is simply 1 over S plus 3. So as in one of the previous questions, you can see that this is a second 2 by 2 A matrix, but what we have got is a first order transformation because of 4-0 cancellations. Alright, so this is fine. Let's just compute one for a 3 by 3 matrix. So A is a diagonal matrix in this case. So maybe it would be easier for you to compute the inverse. Minus 1, 0, 0, 0, minus 2, 0, 0, 0, and minus 1. So just one second. B is 1 0, 1 2, 2 1. C is going to be, so let's just compute Si minus A inverse first. This is simply S plus 1, S plus 2 and S plus 3. Okay. So you already know what the determinant is. Just S plus 1, S plus 2 and S plus 3. And you can also find the adjoint pretty easily for this case, right? So just cofactor Si minus A, you already have this. Let me see. Alright. So for the first one, this is just S plus 2, S plus 3. For the second one, it's just 0. I hope you can see that. So for this one, it's still 0. For this, 0. Then you'll have S plus 1, S plus 3. Then it's 0 again. And yeah, S plus 1, S plus 2. So what okay, so again you can have the adjoint. This is a diagonal matrix, so these are going to be just equal. And Si minus A inverse is going to be, so it is going to be 1 upon S plus 1, 1 upon S plus 2, 1 upon S plus 3. So the main point is that the inverse of the diagonal is just inverse of each of the diagonal elements. So you can write this down very easily. And from next time, if you can just observe that this is diagonal, then you don't have to compute this adjoint anymore. Alright, so we have Si minus A inverse. Let's just write down this quickly now. D is still 0. Okay. So let's see. C is going to be 1 1 2. And we have 3 by 5. Then a 3 by 3 matrix. And then finally B. So this is a multi-input, multi-output system. So G, sorry, this is 2 1. Okay, so can one of you compute and just let me know what the answer is? And then we have 10 over S plus 3. And the last one is just simply plus 5 over S plus 3. Okay, so you can just take this out common. And this becomes, so you can simplify this. So let's just do this quickly. Okay, so let's see. This becomes plus 2s plus 3 plus s plus 1 s plus 3 plus 4 times s plus 1 s plus 2. And the next one is simply, there are only two entries, so s plus 2. This is also clear. Okay, so you need to multiply s plus 1 from here because we have already taken this one out. So times s plus 1. And then this entry is just s plus 2 s plus 3 plus okay, so you can simplify this further and you get the transfer function gs. So this would be a 2 by 2 system again, or the ratio between the first output, second input. Then, okay, so let me just write this down in the matrix form. And then you have y2s over u1s and y2s over u2s. So this is exactly this. Okay, so I hope these are enough questions for you to know how to convert a state space model to a transfer function. Okay, so if this is here as a practice, and you can try out these ones. So the first one is, so I'm just writing down the matrices directly. So this one is a simple second order system and also with a diagonal A matrix. Then we have 2, 5 and say 0, 1. And then we have a third order system. This is 0, 0, 0, 1, 0, minus 3, 0, 1, minus 4. This is going to be 40, 10 and 0. So for this you can either use the algorithm or just compute Si minus A inverse using algebra. It's your choice. Alright. So the next topic we have is on the computation of state transition matrices. So as we recalled in the introduction that the state transition matrices are required for solution of, for example, this kind of homogeneous system without the input. So the solution for this is, so if A is a, so this is an LTI system, A is a constant matrix, then it would be H0. So for the LTI system, this is the state transition matrix 5T. Alright, and to compute phi of t, instead of taking the exponential of the matrix, what you can do is compute this Laplace inverse of Si minus A inverse. Alright, so we have already seen many times now how to compute this inverse, and the extra step here is just to get the inverse Laplace transform. Alright, so let's see. This is question number 6. Alright. So it's for the following system. X dot is this one, second order system. X1 dot x2 dot equals. Okay, so for a homogeneous system, let's just remove this one. This is 0, 1, minus 2, and minus 3. Okay, so you have one option. You can either compute this. This is at plus a square t square by 2 factorial, and it's a infinite series. Or what you can do is just compute si minus a quickly. So it's 0, 1, minus 2, minus 3. This is simply s minus 1, 2, 1, s plus 3. Let's see, it is going to be s square plus 3s plus 2. And you can just interchange these entries and then reverse the signs. Okay, so this is, let's just not write this down again. Okay, so what you need next is the Laplace inverse of si minus a inverse. So this is just Laplace inverse of each of the entries. Alright, so let me just write this down once. So for this you need partial fraction expansion of the denominator. So let's see. Let's check. This equals minus 1. So 1 minus 3 plus 2. Alright. So s plus 1 is a root, and I think s plus 2 is another one. You can check. 4. This is plus 2. Yeah. So this is s plus 1, s plus 2. Okay. So let's check. Okay, so you can observe that these and these just differ by a constant in the numerator. So what I will do is just s squared plus 3s plus 2. So just find out the Laplace inverse of this quantity. This is c1 over s plus 1 plus c2 over s plus 2. So you can just find out the constants pretty easily. So c1 is 1 over s plus 1, s plus 2 times s plus 1 evaluated at minus 1. This is just 1. Similarly, you can compute what c2 is. This is just 1 upon s plus 1 computed at minus 2. This becomes 1 over s plus 1 minus 1 over s plus 2. So these are fine now. The Laplace inverse of this. So this is going to be e to the power minus t minus e to the power minus 2t. So I hope you know how to calculate these inverse Laplace transforms. Alright, so this is here. We have two more terms. Okay, so you can observe that in this we have already computed what 3 over s square plus 3s plus 2, the Laplace inverse of this is going to look like. So we just need to compute Laplace inverse of s over s square plus 3s plus 2. Okay, so let's see now. We have just let's see it's s over okay. S over s square plus 3s plus 2. Just a second. Yes. So again, it's going to be s over s plus 1, s plus 2. It's a strictly proper transfer function. This is just going to be c1 over s plus 1, c2 over s plus 2. So let's compute these coefficients quickly. S over s plus 2 evaluated at minus 1, s over s plus 1 evaluated at minus 2. So this is minus 1, this is 2. Okay. This becomes minus 1 over s plus 1 and just 2 over s plus 2. So this is nothing but, sorry, this is L minus 1 over s plus 1 plus 2 over s plus 2. This is simply minus e to the power minus t plus 2 into e to the power minus 2t. Now let's just write down what the state transition matrix is going to look like. Okay, so let's go back up. So this is going to be just quantity again, and plus 3 times, so let's remove this, 3 times this quantity. So e to the power minus t minus e to the power minus 2t. Then we have the next one, and it's just 1 over this. Okay, this is easy, it's going to be then we have the next one, it's just minus 2 times e to the power minus e to the power minus 2t, and this is s over. So this is simply minus e plus 2 to the power minus 2. Okay, so this is going to be, I just simplify them a little bit. This is still the same. Okay. So this is the state transition matrix for the given system. So now this is there, let's see the next question. This is question 7. Okay. Okay. So we have first homogeneous system given by the A matrix. So then what is the state transition matrix for the system? So this is similar to the question that we just done. So let's compute. So I just Si minus A first. This is S minus 1 plus 6 is plus 5. Now this is simply plus 6 s plus 5s and then minus 6. Let's just factorize this first. So this would be, let's check, minus 2, I guess. So 4 plus 6 and yeah. So let's see, s square plus 5s plus 6 and s plus 2. This is just simply 3. Okay. So we have this as s plus 2, s plus 3. Okay, so let's see Laplace inverse of 1 over s plus 2 and s plus 3. And the other one that we need to find out is s over s plus 2, s plus 3. Okay, so let's just find this out quickly. So this is going to be upon s plus 2 and s plus 3. So this calculated at minus 2, this is 1, and then minus 1. So then we have s over s plus 2, s plus 3, again some constant c1, c2. Let's see, s plus 2 and s plus 3. So the first one is minus 2 over 1, and the next one is 3 over minus 1. So we have minus 3. Okay. So we have these Laplace inverses, and let's just write the state transition matrix now. So this becomes, okay, so sorry about that, the inverse Laplace transform, e to the power minus 2t minus e to the power minus 3t, and similarly we have this. Alright, so we have minus 2 e to the power minus 3 minus 3 to the power minus 3t plus 5 times. Alright, so 5 times e to the power minus 2t minus 5 e to the power minus 3t. Then we have okay, this is simply this, and then we have minus 6 times e to the power minus 2t to the power minus 3t, and then we have minus 2 e to the power minus 3. Alright, so you can simplify this further in the first entry of this. This becomes 3 to the power, okay, so this is 2t, I guess. Yeah, sorry about that. 2t, and this is also 2t. Okay, and then we have 8 minus 3t minus 6 and plus 6. Okay, so I think as the last question, what we can do is compute the state transition matrix for a 3x3 system. So let's see, and as of this question, you can have the second part. You can calculate the second part of this, where this is simply, this is still a second order system. compute the state transition matrix. Alright, now we have a third order system. So x dot is 0, 0, minus 2, 0, 1, 0, minus 0 and 3 times x. So we need to compute the state transition matrix. Alright, so t is let's see. Let's compute si minus a. So this is 0, 0, minus 2. Okay, and we have 0, s minus 1 still 0, minus 1, 0, 1, s minus 3. Alright, so determinant is okay. So we can compute the determinant by expanding along this column. So let's see. This is 0 and this becomes okay. So s minus 1 times s minus 3 plus 2. This is going to be s square minus 3s plus 2, s minus 1. Okay, so let's just decompose this right here. So okay, so this becomes 1, this becomes plus 3 plus 2. Let's check if plus 1 is a solution. Alright, so let's see. This is going to be 1 plus 3 and plus 2, so this is in 0. We have s equals 1, so we have 1 minus 3 plus 2. Okay, so we have s minus 1 as the root. Now let's see. The other one could be so this is s minus 1 and s minus 2. Okay, so you already have the determinant in the factored form. Now si minus a inverse is okay, so let's compute the joint now. This is actually the cofactor matrix of s0 to 0, s minus 1 0, minus 1 0 and s minus 3. This is s minus 1, s minus 3. And we have s times s minus 3 plus 2. So the negative of this. And then we have s minus 1. The next entry is 0. Then we will have this one is 0. Let's see. Yes, and then the last entry here in this row is 0. Okay, now for the last row we have 2 times s minus 1, and this is going to be negative of, so here, and so this is just 0. Let's see. And for the last element we have s times s minus 1. So you can take the transpose of it. So I'm just going to write this down directly. Si minus A inverse is s minus 3 over s minus 1, s minus 2, 0, minus 2 over s minus 1, s minus 2. You can just recheck this. 0, 1 over s minus 1 and 0. Then this is 1 over s minus 1, s minus 2, 0 and s over s minus 1, s minus 2. Now all we need to do is take the Laplace inverse of it. This is going to be easy. You need to find out Laplace inverse of this and the Laplace inverse of s over s minus 1, s minus 2. Okay, so let's see. So C1 is going to be 1 over s minus 2, value at 1. This is minus 1. C2 is going to be 1 over s minus 1, valued at 2. So this is minus 1 over s minus 1, plus 1 over s minus 2. So the Laplace inverse becomes minus e to the power plus t plus e to the power 2t. Okay. Okay, so there is just one more term. This is easy to calculate. Laplace inverse of 1 over s minus 1 is simply e to the power t. We have s over s minus 1, s minus 2. This is c1 over s minus 1, this c2 over s minus 2. So c1 is s over s minus 2, consider that 1. So this is consider that 2. Okay, so this becomes minus 1 over s minus 1 plus 2 on s minus 2. And the Laplace inverse becomes minus e to the power t plus 2 to the power 2t. Alright, so now let's write down the state transition matrix. We have so s over s minus okay, so s over s minus 1 s minus 2 is this. Then we would have minus 3 times, then we have 0, then minus 2 times. Okay, so again we have zeros, and there is e to the power t. Then we have 1 over s minus 1 s minus 2, so this is simply e to the power plus t plus e to the power 2t. Then we have 0, and this is simply e to the power minus t plus 2 e to the power 2t. So just let's simplify this. Alright. So this becomes 2 e to the power 2t minus e to the power 2t, then 0 to the power t e to the power 2t. So this is the state transition matrix. Now in addition, if you have been given that there is some initial condition, for example 0 1 0, then the solution of x dot equals ax with a given above at some time t is given by xt is actually equal to phi of t times x0. So you can, for example, some x at 1 second, you can compute the state transition matrix at t equals 1 and then substitute this step. So you get the solution of the state space homogeneous state space equation at t equals 1. Okay, so I hope this was clear to you. Let's just quickly recall what we did today. Okay, so we mainly dealt with these two, the state space to transfer function conversion and computing the state transition matrix. Alright, so let's see. So we had a simple second order system. We saw how to compute the adjoint for the simple second order system, and then we found out what GS was. Then we had a similar question as part B, and then in part C we could see that although this was a 2 by 2 matrix, the transfer function that we got was of the first order, so due to 4-0 cancellation. So in this question we also noted that there were two transfer functions, two state space representations. So for example, this was 1, this was 2, and we saw that these are the same transfer functions. So there's a remark that the transfer function of a model is unique, however the state space model is not. Okay, and as a practice question you can check again that this state space representation has the same transfer function. So then we moved on to deriving the transfer functions for the third order system, and the main point here was to compute Si minus A inverse. So there are two approaches: either compute the adjoint of the matrix or use the algorithm that was discussed in class. So this is steps of the algorithm. So since this was a third order system, we just need to calculate P1, P2, P3 and A1, A2, A3. So these are just computations, and this is the transfer function. Oh, sorry, Si minus A inverse. You can substitute A1, A2, A3 computed, and the matrix is P1, P2, and P3. And since this was a multi-input, multi-output system, you get GS as a 2 by 2 matrix, which has these components. So the ratio of each of the outputs with the both inputs U1 and U2. Okay. So then again we had a 3 by 3 system, and in this case Si minus A was computed using adjoint of Si minus A. So you can see the steps here. We first computed the determinant, then we computed the cofactor matrix, we took its transpose, and then we simply had Si minus A inverse. Now let's see. Again we saw that a system with two states has a transfer function of first order. And then for the 3 by 3 system, we looked at a diagonal A matrix and said that the Si minus A inverse is simply 1 over the diagonal elements. Okay, so this was also the multi-input, multi-output case. Next, we looked at how to compute the state transition matrix and its application in finding the solution of the homogeneous state space system. This is simply Laplace inverse of Si minus A inverse. So for a second order system, this is simply Si minus A, and what you have to compute is Laplace inverse of each of the entries of the 2 by 2 matrix. So this is what we did here. These are just computations on how to find out these constants in the partial fraction expansions. And then we saw third order system. So we had 3 states, and the objective was to compute the state transition matrix. So again the question is on how to compute the inverse of Si minus A. So for this case we just computed the adjoint, and we saw that this is Si minus A inverse. And then similar to the previous question, the Laplace inverse of this matrix is Laplace inverse of each of the entries. So again we are finding these coefficients C1, C2 in the partial fraction expansions, and we got this as a state transition matrix. And for the solution of x dot equals A of x at some time t, for example 1 second, this is going to be the solution given this initial condition x. Alright, so I hope that this session was helpful to you. So let's end it now.